Now we're going to do some analysis based on functions that we have in Mathematica, and you have all this code, so you should be able to reproduce everything that's here. So we're starting with a function f of x that is x to the fourth plus 3x cubed. So one thing to note is that this is a polynomial, and we like polynomials because they're continuous everywhere, and they have they're differentiable everywhere, so they have nice properties. So we first just graph the function, and one of the things that we're doing is trying to figure out where the function has maxes and mins, where it has inflection points. So we graph the function first, just kind of get an idea of generally what it looks like. We can see a minimum value here, so we're going to try to find exactly where that is at what x value. Looks like we have a horizontal tangent line here at the origin, and clearly the function changes its concavity. It starts out concave up, and then again I'm not exactly sure where, but somewhere it changes from concave up to concave down, and then maybe right here it goes back to being concave up. So we're going to use all the ideas from sections 4.2 and 4.3 to try to figure this stuff out. So we find f prime, which again, this is a nice easy polynomial, so you could find f prime very quickly yourself, but the computer can find it as well. So when we're solving, setting the first derivative equal to 0, we're looking for maxes and mins. And we see we get really two unique solutions, x equal 9/4 and x equals 0 is repeated. And so what I've done here is make a little table of values of the first derivative, right, derivative values of f. And of course, we see where the derivative equals 0. We already knew that. And then we're checking the sign, SIGN, of f prime on either side of that. So if I were doing this on paper with my calculator, this is the way I would do it. I'm going to write down the critical numbers that I found where f prime is 0, and I'm going to check the sign of f prime to the left of negative 9/4. That would be negative. Okay, so it's this -3, -27 that gives me the negative value for f prime when x is less than negative 9/4. And then f prime becomes positive. I test an x value. Actually, let me use a different color for this, and maybe that will help so you can see the difference. I pick an x value in between negative 9/4 and 0, and I picked -1. That's not the only one you could have chosen. And I see that I get a positive 5 f prime value, so my derivative then is positive. And then to the right of x equals 0, I can put another positive value because I tested an x value to the right of 0. I tested x equal 1. And the y value I got for f prime was positive. So putting this together, I know that f is decreasing to the left of negative 9/4, and then it's increasing, and then continues to increase after x equals 0. And I can compare that to the graph I have. So there is a relative or local minimum at x equal negative 9/4. That would be right here. So again, at negative 9/4 there is a minimum value. I don't know what the value of the minimum is. I don't know what the minimum is. I'd have to evaluate and find f of negative 9/4 to figure that out. But notice I have a horizontal tangent line. So in fact, the slope is 0. And then at x equals 0, as I conjectured before, I could see it in the picture. Slope is 0 when x equals 0 as well, but that does not correspond to a max or a min. The graph is increasing to the left and still increasing to the right of that spot. So this is basically the first derivative test. Then I evaluated f double prime at both of those critical numbers, -9/4 and 0. And notice how I put those in brackets separated by a comma, so it takes up less vertical space on the page, but you could evaluate each one separately. But basically what I've found here is that f double prime, well, actually, let me go back. Up above, I found that f prime of -9/4 is 0. And I've also now found that f double prime of -9/4 is positive, 81/4 positive number. Therefore, f has a relative minimum at x equal -9/4. So that's the second derivative test. And in the second case, I have f prime of 0 equals 0 that I found up above, and now I also found that f double prime of 0 equals 0. That is neither a max nor a min. And so I'm going to want to investigate a little further at x equals 0. Now, a plot of f prime, I'm going to just go over a couple quick things, but I encourage you to spend a little more time comparing f and f prime and remembering what we did back in chapter 2. So here I have a root on f prime that is at -9/4, and what we had done back in chapter 2, looking at where the derivative is negative, my function f up above is decreasing. And then I have a root on my first derivative at x equals 0, where f prime is positive above the x-axis, f is increasing. So again, just relating the f prime to the f. Alright, so then I want to find possible inflection points. I take my second derivative, which again I've just asked the computer to find for me, and I've set that equal to 0, and I get two solutions, x equal -3/2 and x equal 0. And so again, I've created a little table of values where I check the sign, SIGN, of the second derivative on either side of these places where the second derivative is 0. And I could also, if I were doing this on paper, I would probably set up a little number line like this, indicating where f double prime is negative, and then check the sign on either side. To the left of -3/2, f double prime is positive, as indicated by the positive 12. In between x equal -3/2 and x equals 0, f double prime is negative, as indicated by the -6. And then to the right of 0, f double prime is positive, as indicated by the positive 30 that I get when I let x be 1. So again, I basically pick one x value on either side of each of these places where f double prime equals 0, and I plug that into f double prime to check the sign, SIGN of f double prime. And what does that tell me about f? F is concave up to the left of x equal -3/2. It's concave down in between -3/2 and 0. And once again, concave up to the right of 0. So I have inflection points at x equal -3/2 and x equals 0. So again, if I go back to my original function, let's see, -1.5 is right here. This is a point of inflection, so that's where f is changing from concave up to concave down. And then I have a point of inflection here at x equals 0, where f is changing from concave down to concave up. Okay, and then again I put a plot of f double prime here just by way of reminder. So here's -1.5, and I'm going to just compare f double prime to f here, where f double prime is positive, f is concave up. Where f double prime is negative, f is concave down. But I also encourage you to compare these to the f prime up above, right? Where f double prime is positive, f prime is increasing. Where f double prime is negative, f prime is decreasing. Where f double prime is positive, f prime is increasing. So again, just keep in mind the same relationships that hold between f and f prime also hold between f prime and f double prime.